Hello guys. So now we are going to analyze the non-prismatic beam element. Okay. So what is mean by non-prismatic? Non-prismatic means the cross-section area of the beam is not uniform. That we call as a non-prismatic beam. So the figure is given in the question like there is a one end that is fixed and another end are fixed. Okay. And the beam which having two members but different cross sections. Okay, let us say this is a member 1 and this is a member 2, like that it is mentioned in the given figure, and their length for member 1 is 4 meter and for member 2 it is mentioned as 3 meter or the length, and the load which acts on the beam at member 2, that is UDL, is acting here for a member 2. Okay, with a value of 20 kilonewton per meter. This is the load which is acting on the beam. So here we are neglecting the axial deformation for this problem. Anyhow, for a beam, generally the axial deformation will be neglected. Okay, and the connectivity, like here it is connecting from node 1. Okay, so for node 1 and node 2 and this is node 3. So three nodes are connected. So connectivity for the member 1 it is from 1 to 2 and for member 2 it is from 2 to 3. Okay, hope you understand. Now the nodal data likes the x value for all the three nodes, it will be x value will be for node 1 it will be 0, and for node 2 x value will be 4 meter, and for node 3 the x value will be 4 plus 3, that is 7, and y value will be 0. Anyhow, of course it is all for all the nodes, it will be 0. That is a nodal deformation. And the given data for the members 1 and member 2. So for member 1 the area for the element 1 it will be A, and for member 2 it will be again A. Okay, so it is in meter square, both the area for member 1, and these are the length. Anyhow, you know, this is, let us say, L1 and this will be L2. L1 L2 will be, and material properties, Young's modulus is given, like E constant value is given in the question. So now you have to make the analysis of this beam element. Okay, so first, as you know that for a beam element the stiffness matrix, element stiffness matrix we have to calculate. So that value for both the members, then we are going to add in the global stiffness matrix. First, the element stiffness matrix general formula I am going to write, that is K is equal to EI by L cube. Again there will be 4 into 4 matrix. In the matrix, first row first column 12, and first row second row first column it is 6L. Now 4L square, it is a symmetry, so I am writing the in the symmetry way, minus 12 minus 6L square, again 12, last row 6L 2L square minus 6L 4L square. Okay, so symmetry. This is the general stiffness matrix for a beam element. Okay, now we have to substitute the value of E, I and L. So as I told you, the material property Young's modulus, which is given as E, and moment of inertia will be I, and length will be for element 1 it will be 4 meter square, when you are taking as 1, K1. When you are considering K2, it will be 3 meter. For L1, it is 4 meter, and for L2, it is 3 meter. So equation it will be changed, like here there will be L, wherever there is an L, it is placed replaced as L1 for K1. Similarly, if it is for 2, it will be taken as 2. Okay, like if you start K2, then it will be L2, L2, L2. Okay, so you have to substitute wherever there is an L for member 1 and member 2. Okay, so after that, after K1 and K2, we are going to make, okay, so we are going to make the addition of K1 plus K2. Whatever you are getting the K1 and K2, that we are going to make the assembling. Assembling is nothing but this is called as global stiffness matrix. Adding both the stiffness matrix or both the members we call as global stiffness matrices. Okay, so there is an procedure to make the global stiffness matrix. In many of the video or made a separate video on this, so you can find out in the playlist. After that, we are going to add this by using K as equal to K1 plus K2. So one thing you have to remember while adding, so whatever the outside the matrix, that let us make single value as a constant value, or same value should be outside the matrix, and whatever the values is remaining, that you can take inside. Okay, then it will be a common for both the K1 and K2. Now after finding K1 and K2, you are getting the value of K. Okay, you are getting the value of K. So this you can obtain from here. Now what it's the stiffness matrix is defined. What the stiffness is? Stiffness is equal to force per unit displacement. Okay, so K is equal to force per unit displacement. So that you can directly write as where K into U is equal to F, you can write here directly. Okay, so now you obtain global stiffness matrix as K, and U will be the displacement vector and force will be the load vector. So K it obtained as like this. Okay, so if nodes are 3, then you are getting the 6 into 6 matrix. Okay, that is the global stiffness matrix you are getting. And the displacement vectors, here it will be U1 to up to U6 you are having all the displacements. And force vectors, so for beam element there will be F1 and there will be movement. Similarly F2, M2, like that you are getting at each node. Okay, so now I will explain here what is boundary condition. That is very important to understand. Boundary conditions. So according to this problem, what are boundary condition you are getting? So here for the node 1, there are 3 displacement in general, but we are neglecting the axial deformation. That becomes we are neglecting. Okay, so there will be only vertical deformation and also there is a slope. So vertical it will be U1 and slope will be U2. And at node 2, vertical will be U3 and slope will be U4. And at node 3, vertical will be U5 and slope will be U6. So in this figure, both the ends are fixed. It means there will be no vertical and there will be no slope at the node 1. It means U1, U2 it becomes 0. And similarly at node 3 also U5, U6 it becomes 0. Okay, so that you have to write here is equal to U2 is equal to U5 is equal to U6. So all the nodes displacement it will be 0 because in fixed. right? So after applying the boundary condition, see the u1 u2 you are getting cancelled, and their column also you are getting cancelled, u1 and u2. And similarly for u5 u6, so u5 u6. So what will be the remaining here? There will be u3, sorry, there will be u2 and there will be u3. In row also there will be u3 u sorry there will be u3 and u4. u3 and u4 will be the remaining. So you are getting an 2 into 2 matrix with a displacement of u3 u4 u3 u4. So these are the unknown displacement, you have to get it. So this is the value of k, okay, global stiffness matrix, and displacement here it will be u3 and u4. And force will be as per the diagram. So there will be here, there will be m3 and there will be, sorry, f3, there will be m3. Okay, so for the particular diagram, if it is an simply supported beam having UDL loads is acting at the member 2, it means for node 1 this becomes 0 0, okay, for the node 1, and the load is acting at the node 2 and node 3. Okay, for node 3, node 2 it will be WL by 2 for F3, okay, and sorry, it is for node 1 F1 F2 it will be 0, and it is F2 here, F2 M2, F3 to 0, okay. Now moment will be L square by 12, okay. So this you are getting, and the load vector, finally the load vector Pf is equal to, for F2 it is the direct load minus the equivalent load. So equivalent will be taken as PE or FE you can take. So direct load 0 minus this F2, and again for M2 also 0 minus M2. It means here it will be minus W minus WL square by 12, minus WL by 2, and M2 is equal to minus WL square by 12, that you are getting. Okay. So now here you substitute the load for UDL and length for the span of the UDL. So you are getting the U3 and U4 values here. If you make the matrix multiplication, these two unknown displacement you are getting from this problem. Okay. So in this way you have to calculate. Here I told you only the general procedure, but when you substitute the value, so you are getting the exact value for this problem. Okay. Thank you.